Okay, so for chapter 38, we're going to do 4 problems. The first one we want to do is problem 16. So problem 16 says we want to find the maximum kinetic energy of electrons ejected from a certain material if the material's work function is 2.3 eV and the frequency of the incident radiation is 3 times 10 to the 15 hertz. So the incident radiation, meaning that the incoming photon, it has a frequency of this value. So just based on this, we would know the energy of a photon. So the situation is like this. So you have this, you have the incoming photon, and then incident on this material, and the material has a work function that's 2.3 eV, and then after interaction, after a photon, interact with the material, there might be a chance for the electrons to be ejected. And when the electron gets ejected, it will come with the kinetic energy. So we want to find out what is the maximum kinetic energy of the electron, given the energy of the photon, and given the work function that's given. So the first thing to do is that we need to figure out what is the energy of the incoming photon, and then based on the conservation of energy to calculate maximum kinetic energy. So first of all, let's calculate E. So E, we will use HF to calculate, the work, to calculate the energy of the photon. And for H, it's kind of painful to write the numbers with the mouse. So it will be, let me just read it. So H, I will use 6.63 times 10 to the negative 34. So let me write it again. So it's 6.63 times 10 to the negative 34, and then times frequency, and frequency is this value. So when you multiply them together, you get the energy value that is about 1.989 times 10 to the negative 18 joules. Okay, 18 joules. Yeah. Okay, so that's your energy, and then we can convert it to EV. So to convert this value to EV, just divided by 1.6 times 10 to the negative 19, then you will get your energy that's equal to in EV, that is equal to 12.43 EV. Okay, and so once you have your E, and we know that you have the work function that's 2.3 eV, so the difference, because the energy is equal to kinetic energy plus the work function. So once you have this, and once you have this, you can calculate the K. So your K value, you will have the K value that is about 10.13 EV. Okay, sorry about the handwriting, just so difficult to write with the mouse. So it's about like 10.13 EV, and if you convert it to joules, you'll be so you will multiply this number by 1.6 times 10 to the negative 19, and the answer will be 1.62 times 10 to the negative 18 joules. So either way, either you express the kinetic energy in EV or in joules, that'll be fine, so long as everything is consistent. So I want to emphasize that the Planck constant comes with the 2 different units. So which number to use really depends on what unit you choose to do. So you just have to be a little bit careful when you do the problems. Make sure that you're conscious about which one that you use. Okay, and make sure that the units are consistent. Okay, all right. So see. So this is the typical problem for the photoelectric effect. And as you can see, the energy of the photon is greater than the work function. So photoelectric effect can occur. if and also, you know, for this one, it also the electron also can, you know, will have a kinetic energy. Now, if the energy of the photon is less than the work function, then a photoelectric effect will not occur. Okay, so that's problem 16. And the next one I want to do is problem 40. So problem 40 says, what is the maximum kinetic energy of electrons knocked out of a thin copper foil by Compton scattering of an incident beam of 17.5 keV X-rays? Assume the work function is negligible. So you can see that this problem, because it talk about Compton scattering, so we're going to use the Compton, the equation associated with the Compton effect and also the Compton experiment. And this is a little bit, this is different from the photoelectric experiment because in the photoelectric effect, you have to consider work function. But for Compton effect, if you look at the energy of the incoming photon, which is in the X-ray range, which is in keV, it is much greater than the energy of a work function. So in that sense, you can ignore the work function. Okay, so the diagram will look like this. So you will have a target, and you have the target, and you have the incoming photon, and then and then there's going to be an outgoing photon, and then there's kinetic energy. So again, you can see that the diagram is actually similar to the diagram for the previous problem. The difference is that this involves a much higher energy of incoming photon. Okay, and it is the Compton effects that that is the focus of this problem. So your E, the incoming energy, I'm going to use E, which has this value. Okay, and with that, it is associated with a wave, because we're going to treat this we're going to treat this photon as a as a wave. So you have this wave number, and let's say the outgoing after the collision with the target, there's outgoing outgoing photon with the wavelength, let's say lambda prime. And then you're going to have the electron is going to pick up the rest of the energy. Okay, so we're going to find the maximum kinetic energy in this in this case. So the question is, under what condition will we consider that the kinetic energy will be a maximum? So so the first thing first, we know the energy is 17.5 keV. We need to figure out what the lambda is. So when you do this, so your lambda is can be calculated using hc over E. Okay, h is the Planck constant, E is the speed of light, and E is the energy. So so in this case, I am going to so you can you can use the Planck constant that's in the EV using the EV.S unit, and then because your energy is given in EV, so they cancel, so everything is consistent anyway. So let me try to write it down here. So my H, I will use this value 4.14, and then times 10 to negative 15, and then times the speed of light is still 3 times 10 to the 8th, and then divided by the 17.5, and it is in keV, so remember to multiply by that by 1,000. And you can see that because this is in EV, that's in EV, so EV just get canceled. So what after you do this, you'll get your wavelength that's in meters. So so it's consistent. So I will get my wavelength, which is 7.097 times 10 to the negative 11 meters. So that's my the wavelength of the incoming photon. And we don't know the wavelength of the outgoing photon, and we don't know the maximum, we don't know the kinetic energy of the electron. But the key word here is that we want to find the maximum kinetic energy. So the equation that that would determine whether whether the kinetic energy of the electron is a maximum or anything other than the maximum will be using the Compton shift equation. So the Compton shift is defined as delta lambda, which is the outgoing wavelength minus the incoming wavelength, okay? And that's also equal to H over MC, and then times 1 minus cosine, cosine phi. So in that case, you can see that we only calculate lambda, we don't have lambda prime. But then we can actually use this equation to calculate, to infer lambda prime, because H is a constant, M is the mass of electron, C is a speed light, and this angle, how do we determine whether the electron has the maximum kinetic energy is determined by the angle, because if the angle, so let me backtrack. In order to find out the maximum kinetic energy, because let me write down another equation from the conservation energy. The incoming energy is equal to the outgoing energy of the photon and then plus the kinetic energy. Okay, so in order for this to be the max, we know that this has to be the smallest as possible. For this to be the smallest, then the wavelength has to be the longest, because wavelength and energy are inversely proportional. So if we want this to be smallest, meaning that your lambda prime has to be largest, and using this equation, we know that when phi is equal to 180, that will give us the maximum lambda prime. So, and that is the condition we're going to use. So when this is 180, you have so you have negative 1, that becomes 2, meaning that your delta lambda is equal to 2h over mc. So our Compton shift is this value, and you can and then this is also equal to lambda prime minus lambda. So in other words, you can actually calculate your lambda prime, which is just the original wavelength, and then plus this 2h over mc. Okay, so my h, when I do this problem, my h here, because I don't, mass is in kilogram and c is meter per second. So the h here, the unit I should use should be in the SI unit. So my lambda is this value, 7.097 times 10 to the negative 11, and then plus 2 times 6.63 times 10 to the negative 34, divided by the mass of the electron, which is 9.11 times 10 to the negative 31, and C is 3 times 10 to the 8th. So when you plug in the numbers and add the original wavelengths to these numbers, you'll get your lambda prime, which is the wavelength of the outgoing photon. You will get 7.582 times 10 to the negative 11 meters. And I can also tell you that this quantity has a numerical value of 4.85 times 10 to the negative 12. That's a Compton shift. And then adding the Compton shift to the original wavelength, that gives you the wavelength of the outgoing photon, which has 7.581 times 7.582 times 10 to the negative 11. So once we have the wavelength of the outgoing photon, we can utilize these equations again to calculate the energy. So my E prime is equal to HC over lambda prime. Okay, and because all my E here are in the EV, so I'm going to actually use the H value here. I'm going to use the 4.14 times 10 to the negative 15 EV times S, that's the unit, and then times 3 times 10 to the 8th over the lambda prime, which is this value. So after you've done that, you'll get the E prime that has a numerical value of 16.38 6.38 keV. Okay, All right, so it's 16.38 keV for the outgoing photon. So once we have the incoming, 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 so we have the incoming, which is 17.5 keV, the outgoing is 16.38 keV, then we can utilize this to calculate our K. So the K max would just be the difference of these two energy. So when you do that, you'll get your K max. That should be equal to 1.12 keV. Okay, so that's basically how you approach this problem. If the angle is not given, you can, and then the condition is that the kinetic energy, should be the maximum. So in that case, your angle here, should be 180. So once you have that information, then you can calculate the Compton shift, and from the Compton shift, you will be able to calculate the wavelength of the outgoing photon. And then you're going to use conservation of energy to calculate the kinetic energy of the electron. So that's basically how you would do it. So a couple of things that that student can make a mistake. One is that the units are inconsistent, or the KeV instead of EV, student forgot to multiply that by 1,000 to convert it to EV. And also, if you prefer to keep everything in SI unit, you can do that. So you just so for the EV, you just have to remember that your energy has to be multiplied by 1.6 times 10 to the negative 19 to convert EV to joules. So that so then everything will be consistent. Okay, and then if the problem asks you to express the answer in EV, then whatever value that you got in joules, just divide that value by 1.6 times 10 to the negative 19. That will give you the values in EV. Okay, right. So that's basically how you how we apply the Compton's equation to find these quantities. Okay. Alrighty, so the next one I want to do is problem 59. All right, so problem 59 says if the de Broglie wavelength of a proton is 100 femtometers, which is 10 to the negative 15, what is the speed of the proton? And through what electric potential would the proton have to be accelerated to acquire this speed? So basically, we are treating this proton as a wave, and it has a wavelength, which is called the de Broglie wavelength. That is 100 times 10 to the negative 100 so the wavelength is 100 and then times 10 to the negative 15 meters. So this is the information we're given. Based on that information, we need to figure out the speed. So because this is the wavelength, and the momentum and wavelength are actually related to each other. So P is equal to H over lambda, okay? And we also know that P is equal to mv, so that you can see the relation between the wavelength and the velocity. And for part A, you also find the velocity. So our V is equal to H over m lambda. Okay, so the H here, I'm going to use the 6.63 times 10 to the negative 34, and the mass of the proton, if you Google that, the mass of the proton is 1.67 times 10 to the negative 27, and then the wavelength is 100 times 10 to the negative 15. So when you plug in these numbers, you'll get the velocity, which is 3.97 times 10 to the 6 meter per second. Sometimes your numbers may not be exactly the same as mine, and it has to do with the rounding and also what value that you use. Like the mass, if you use there might be there might be a little bit different if you use a different source to get the mass. But anyway, so as long as they are in the in this range, then that should as long as they are in a range in this range, and then you have the same equation, right equation, then that should be fine. So velocity is 3.97 times 10 to the 6 meter per second. This is how fast the proton would travel, and given the wavelength. So then the next question is, through what electric potential will the proton have to be accelerated to acquire the speed? Now we know that if the proton is moving with a velocity, then it comes with the kinetic energy. So so in order for the proton to acquire that kinetic energy, you have to provide energy, and so we can provide the energy through sending the proton through go through the electric potential to accelerate the proton. So in that case, in mathematical form, it just means that the energy of the proton is equal to 1/2 mv squared, that we know, and that will be provided by when the proton is traveling through electric potential. Okay, and if you remember, electric potential is U, and it's equal to the electric charge times the potential difference. So our question is, what is our potential difference here? So your V, so we have the 1/2 and the mass and the V. So the V, we're going to use this V to plug in here. And the M, again, let me just read it again. The mass of the proton is 1.67 times 10 to the negative 27. And then the E here is 1.6 times 10 to the negative 19. So when you plug in this number, you'll find that the potential difference that the proton will have to be, go through in order to acquire that, acceleration to achieve this velocity is 82.25 kilovolts. Okay, and you might say, okay, the numbers that so far I've been given to you, the answers are a little bit different from the ones provided in the answer key, and that is okay because of the rounding and because of the numbers used. So but it is basically the approach is this, and and then when you plug in the number, if you get the in this range, then that is fine. Okay, all right. Okay, so that's basically that. And the next one I want to do is that I want to show you, the Heisenberg's uncertainty principle. And we know that the Planck constant in our world is very small. It's 6.63 times 10 to the negative 34. So that's why even though we can behave like a wave, but we really don't experience that because the wavelength is actually quite large, and the other thing is that and then when it comes to the uncertainty principle, because in our macroscopic world, okay, actually here the problem will actually just tell you. So let me just read the problem. Okay, so imagine playing baseball in your universe, not ours, where the Planck constant is 0.6 joules times second. And thus quantum physics affects macroscopic objects. Okay, what will be the uncertainty in the position of a 0.5 kilogram baseball that's moving at 20 meters per second along an axis if the uncertainty in the speed is 1 meter per second? Okay, so in other words, because in our real world, our Planck constant is so small, so if there's any uncertainty, we don't we cannot detect it. But then if you're in a different universe, and that has a hypothetical Planck constant that's actually quite large, which is 0.6, you'll find that the uncertainty principle, the effect, can be it is substantial. So let's see how we apply the uncertainty principle. We know that it's delta x times delta p has to be greater than h over h bar of h bar, which is h over 2 pi. Okay, so now we want to find this quantity. Okay, so in order to find this quantity, we need to know delta P. We know that the mass is 0.5, and the uncertainty of speed is 1. And we know that P is equal to mv. So delta P is equal to m delta v. So delta P is equal to mass, which is 0.5, times the uncertainty in velocity, which is 1. So this has the numerical value of 0.5 uncertainty. So you have the delta x that is equal to h, which is 0.6, and over delta P, which is 0.5, and then over 2 pi. So when you plug in this number, you'll find that the uncertainty in the position is 0.19 meters. And this is actually detectable. It's quite large, right? 0.19 meters, as opposed to a very small number. So this is one case, just to illustrate, there is uncertainty. When you just, for the everyday life that you play baseball, if there's uncertainty in the speed, then you can't pinpoint where the ball will be landed. Is subject to this uncertainty. Okay, so that's basically these are the problems for that we went over in chapter 36. Okay.